Thank
All right,
you.
well, thank you. Let me go to the beginning here for some reason. So this is going to be a very broad brush, kind of general look at observing magnetic fields with interstellar polarization. And I'm going to be emphasizing far infrared polarimetry of galaxies using Hawk Plus towards the end, right? Now, interstellar polarization was discovered in 1949 independently by Hall and Hiltner. And if you look across spiral arms to distant stars, for example, towards Perseus, you can see that the polarization half vectors are very consistent and smoothly varying in the plane of the galaxy. Whereas if you look down a spiral arm towards Cygnus, for example, you get a much more chaotic geometry. And this was one of the first very clear indications that it was the interstellar magnetic field that was controlling the position angles for these polarization half vectors. All right, now what's going on? Well, if you take interstellar grains, which are not round, they're little flat things or long cigar things, and you orient them so that they are long axis perpendicular to the interstellar magnetic field, you can see that if you have a distant star, the light shining through, the light that's polarized in the horizontal plane will be more absorbed than the light polarized in the vertical plane, and you will get a net polarization in the vertical direction along the magnetic field. Now, in emission, these dust grains, which are warm and emitting in the far infrared, will emit more in the horizontal direction than the perpendicular direction. And so the polarization and emission will lie at 90 degrees to the magnetic field. It's almost always the case that papers using far infrared polarimetry rotate the position angle by 90 degrees to the preferred or expected or inferred magnetic field direction. And there are references, there's a list of references at the end of the talk. I'll put that up so you can see what all these references go to. All right, now the current leading theory for how we align the grains is called the radiative torque alignment. If you want to look into it in all of its gory details, start with this review paper down here. Basically, you have an interstellar dust grain, which is not spherical. It has a net helicity, which I have modeled by using a fan blades. That's a little extreme, but it gets you the idea. The interstellar radiation field can be asymmetric. There's more coming from, not from this direction, but this direction, and there'll be a net difference in left and right-hand circular polarization that will spin up your grain. If you spin a paramagnetic substance in the presence of an external magnetic field, it will induce magnetic moments in the grain, and that means that the grain will get magnetized and it will precess around the magnetic field direction. As this grain precesses, the geometry of the helicity will change with respect to this net polarization in the interstellar radiation field, and whiz, bang, boom, a miracle happens, and the grain will align with its rotation axis along the magnetic field axis. Okay, that's all I want to talk about for the mechanism. Now, how do we know it's the magnetic field? Well, I just gave you one example, but this is just one of many examples you can create by just looking at data. So here is optical polarimetry of stars shining through a high latitude cloud in the Milky Way. So we're looking up out of the Milky Way, and here's the synchrotron emission, which is polarized, and it's nicely perpendicular to the optical polarization, which was exactly what you would expect if magnetic fields are responsible for the alignment mechanism. I'm not going to go over this completely because you just saw the previous talk about Hawk Plus data, but I do want to point out that in in raw form, Q and U are intensities. They are not fractions, they're intensities, and they can be negative. All right, so if you have no net polarization anywhere in your map, Q and U in principle will distribute about zero. However, the polarized intensity, which is the square root of the sum of the squares, will always be positive, even if you have no polarization whatsoever on average. So just keep that in mind. That's sometimes called polarization bias, and I'll talk a little bit about it, but not much more, but it's something to be careful about. The fractional polarization is the polarized intensity divided by the total intensity, and the position angle measured east of north, north up, east to the left, is given by this formula. And so if you're using Python or some other more fairly modern, even Fortran like me, you want to use ATAN2 so that this ratio ends up in the correct quadrant. All right, quick little note that the P, that's fractional polarization in extinction, goes like hyperbolic tangent of tau P, the polarization optical depth, which is about tau P for modest sizes of tau P. In emission, polarization and intensity, the polarized intensity is tau P times the Planck function, and if optically thin. So the polarized intensity in the far infrared is proportional to the fractional polarization in extinction. And if you want more on that, look at the appendix in that paper there. Okay, so we often describe the interstellar, the interstellar as well as any other place, magnetic field as being made up of two components. We do this because it simplifies our way of our use of the data to analyze what we think is going on with magnetic fields. Magnetic fields are much more complicated than that, but nonetheless, we take a slowly varying component, either down the beam or across the beam, and we call that the coherent component. And then we take the little wiggles on that, which we will call the turbulent or random components to these. So this could be a spiral arm feature. It could be an hourglass feature in the collapse of a molecular cloud. And then there's turbulence on top of that little feature, and we divide them into these two quantities. And Jordan is going to be talking next on this sort of topic. Now, if we look down a line of sight and everything is perfectly aligned, well, that's great. We get good polarization and we get a position angle and we know what the magnetic field is doing. We can look down a line of sight with a lot of turbulence. The turbulent component is wiggling all things around, and we don't get much polarization. And that shows up, and the position angle is relatively indeterminate in that case. Most likely, we're looking down a line of sight where we have fairly well-aligned grains along the line of sight in some places, and in a region where something else is happening. That could be tangled on short scales. This is what we think is happening in many, many locations in external galaxies and in the Milky Way. It could be that there's a region where there's no aligned grains. If you don't have an interstellar radiation field penetrating down into the molecular cloud core, you can't spin up your grains and you can't align them. That adds total intensity in this direction, but no polarized intensity. Then we could also have a magnetic field that produces a cross Polaroid. In other words, the magnetic field is one direction in front and back, but is an almost perpendicular direction in between, and that will help cancel some of the net polarization. All right, this is a complicated figure. I'm not going to spend a whole lot of time on it, but polarized intensity in the far infrared and emission is plotted on this axis. Polarization and extinction, that's fractional polarization, is plotted in this axis. And this is column density. And we're going to represent column density in the far infrared by the surface brightness, the far infrared intensity. More far infrared intensity means more dust, which means more visual extinction, which means more column density. As we go up in column density for a perfectly aligned magnetic field, the polarization in extinction saturates. You can never have more than 100% polarization in extinction. Whereas in the far infrared, the ratio of the polarized intensity to the total intensity, which is the fractional polarization, stays the same. Now that eventually will also turn over when you get optically thick in the far infrared, but that's only under certain circumstances. Now, if we have a totally random magnetic field along the line of sight, Believe it or not, the polarization in extinction and the polarized intensity do increase with increasing column depth, but only as the square root of the column depth, not linearly. And if you make a mix of those, you get something like this. And this is what we see a lot of places. But this is also what we see in many directions. How can that be? Well, let's look at that for a moment. This is an example of magnetic fields on a small scale. This is from Chet Hull's work. This is an embedded class 0 YSO, a very young protostar. And you can see that the polarization half vectors are very smooth. They vary very smoothly across here. But we have a problem. And the problem is we're not sure if, for example, along this line of sight, we are seeing all the dust grains all aligned, or if there's regions where there's no dust grain alignment, for instance, way downside in the molecular cloud core. Now, that's extremely important because if you don't know where the field is aligned, you can't figure out what's going on with your model of core collapse. And we know that the star and its accretion disk is completely decoupled from the interstellar radiation field and the magnetic field that's out here. That we have to figure out how that happens if we're going to understand star formation. Okay, is there a grain alignment problem? Well, let's look at a bunch of, class 0 YSOs. And let's look, and this is from Galamitz et al., and some of them have a slope in fractional polarization versus surface brightness of -1. That indicates that we're adding total intensity, but not polarized intensity. Is there a grain alignment problem? Polarization goes as I to the -1. Well, we used to think so, but not quite so fast. Recent work by Paddle has shown that if you get into the low signal to noise regime, you have a error in Q and U, and the fractional polarization is this relatively constant error divided by I, so you automatically get P goes like I to the -1. This is a simulation she ran, and where we have a constant 2.5% polarization, a constant error in Q and U, and no dependence on intensity. So at high signal to noise, you get 2.5%. But as soon as you go to low signal to noise, you automatically get P goes like 1 over I. Okay? Now you figure, no problem, I'll just take the highest signal to noise data I've got. Well, if you do that, that's indicated in red, that's 3 to 1 or better. You can see that those are just giving you the extreme end of the distribution about this line. That's the Ricean distribution. So we got to be careful, but there is no position angle information in that analysis. So let's look at that just for a moment. This is some work that my graduate student Jin-Ah Kim is doing. So we put into the model a error in I, Q, and U. We put in intrinsic polarization in the model that does intrinsically go as P over I, constant over I, and we put in a constant position angle. If you look over here, this is the raw fractional polarization, uncorrected for bias, versus surface brightness or column depth. If you look at that red dashed line, that's what you would expect based just on the noise. If you look at the observed, that barely visible blue dashed line, it's a bit above, and that's because we have a net intrinsic polarization. So you can dig out the net polarization that's there intrinsically, but it ain't easy. Let's add position angle to the analysis. So position angle is constant. This axis is the difference between the observed position angle and the input position angle. And this is signal to noise. And you can see as we go above 3 to 1 in signal to noise, this is raw, uncorrected for polarization bias, you can see that the difference becomes small. So in other words, over here, your position angle is much more likely to be correct than over here. And I don't have time to go into this much further, but that's something to keep in mind. Okay, let's go out a bit in scale. Let's go out to molecular cloud. This is work on OMC1 by Chus et al. I show this here at 89 microns to show you that we have some large scale structure in the magnetic field, indicating that it is dynamically important in what's happening in this molecular cloud and in star formation. And again, I keep doing that. Again, see the talk by Jordan that's coming next, where he's going to talk much more about this type of thing. And in a paper by Jordan, Guerra et al. 2021, they were able to find regions where gravity dominated the magnetic field or the magnetic field dominated gravity. If the field dominates, that means the magnetic field lines hold up the gas from collapse, and if gravity dominated, that means that the magnetic field lines are unable to hold up the material from collapse. If you look, you'll see this finger here of gravity dominated region. That's where the star formation is taking place. That's BNKL. And outside that, magnetic field dominates. And a lot of work being done on this. Maybe Jordan will tell some more about that. Okay, so let's look for a moment here at some external galaxies. NGC 891, the classic edge-on spiral. M51, the classic face-on grand design spiral. And M82, the classic starburst galaxy, where you have a tremendous amount of star formation taking place, completely blowing out holes in the north and south poles of that galaxy. Now, a lot of these galaxies have been observed in the radio with synchrotron observations, and they're very complementary observations, but they don't measure the same path. Cosmic rays are everywhere, and if the wavelength is too long in the radio, you can't see past the disk because of Faraday effects. If you're at a shorter wavelength in the radio, say 3 centimeters, for a face-on galaxy, you can see all the way through. But from an edge-on galaxy, you still can't. The far infrared is dominated by warm dusk in the disk. I'm going to leave this slide just in case you go back and look at this presentation later on. And I'm going to go straight to M51. Okay, so there's been a lot of work on M51, and there's some in progress. Kim is still working on it. This is the latest M51 polarization from the far infrared. That's in white, those white vectors, and the radio is in black. And you can see that the radio and the far infrared are pretty close most places, even this spur that goes out over the companion, but in other places they're not. And that's a source of a great deal of work at the moment. In particular, look at Borlaug et al. If you want to see an analysis of that. Now, if you take the raw polarization versus the intensity, and you ask what would I get if it was just pure noise, you would get this. What we observe is the blue, and so the net polarization in M51 can be extracted from this. And Jinnah is working on the polarization position angle information as well, and that's going to improve our understanding of what's going on in that galaxy. All right, let's look at M82. This particular figure is from Enrique Lopez Rodriguez et al., and they've modeled the magnetic field down inside here and extrapolated those field lines out into the intergalactic medium. And you can see that they're basically open lines. And so the magnetic field lines go way out into the intergalactic medium. A very nice result. Let's look a little bit more at M82 at 154 microns. That's these little teal vectors here. You can see the outflow. You can see the evidence of the outflow. But if you look in the disk, in the plane, you can see that the position angle becomes in the plane. And we have crossed polaroids. We have a disk geometry where the field is oriented along the disk, and we have a polar geometry where the field is along the outflow. Now, Patel et al. Observed at 850 microns, which is a longer wavelength and sensitive to cooler dust. And the disk is full of the cool dust, and the far infrared measures the hot dust. And you can see right here that the hot dust dominates along that line of sight, but over here you can see that the cool dust dominates, and you pick out what might be a spiral structure. Okay, finally, NGC 891. This is, we're still working on this. There's a little bit in that paper, but there's a lot more coming. And where the question is, are there vertical fields in this edge-on galaxy? All right, so we have some major challenges. I'm just going to leave that slide up for a moment so you can read it. But grain alignment, we're still not sure where and how grains are aligned. That's still a problem. And we still don't know where and how the interstellar magnetic field and the protostellar magnetic field decouple. That's very, very important. You can't make stars unless the field decouples fairly quickly and fairly efficiently. The traditional ways of leaking the magnetic field out are too slow. All right, now we need to fully calibrate Davis-Chandrasekhar Fermi. That's a method of measuring the magnetic field strength, and something called the structure function analysis, which I didn't have time to talk about today. Jordan will talk about some of that in his talk. Now, we still aren't sure if we could see enough dust to explore galactic halos in these edge-on galaxies, but we're working on that. And another type of galaxy we should turn our attention to are called dwarf starburst galaxies. These are galaxies that are low metallicity nearby galaxies that are small, and they're considered an analog for galaxies very, very early in the universe. So these are our nearby analog to the first galaxies ever born. And maybe the starburst is capable of blowing out so many baryons that you end up with a baryon-starved dark matter halo. Well, the magnetic field might help us find out if that's what's happening. Okay, so there are some references. I will leave that up and finish here a little early, but that's kind of like I do it. Any questions?